Good morning, everyone. My name is Evan Barrett, and these are my team members, Dave and Andrew. And our project is building a Arduino, a drone, an Arduino-powered drone. I just want to start off the presentation by saying, unfortunately, there won't be a demonstration. We're still figuring out a few errors with it. But we learned a lot about it, and we want to show you what we learned, and we have a few ideas of why it's not working, and we'll also explain that to you. And yeah, so Dave will.
We have our background here. So basically, what we're going to explain here with the specifications. So we have two parts. We have the drone itself, and we have transmitter. So we have the Arduino. These are parts for the drone. So we have the Arduino Pro Mini. We have the radio frequency module, gyroscope, motor control board, and fastest buzzer. And for the transmitter specifications, we have the Arduino Nano frequency module as well, the filtered power supply module, and the 16x2 LCD display, and toggle switches for joystick on-off switches. And we also have a drone thrust scale over here. So our drone is specified for light wind operation, and yeah,
So just indoors or on a very mild day.
And then right here we have our transmitters. So for our transmitter, we have our batteries. You have your power stick, you have your two joy stick modules. You also have your transmitter, your filtered power supply for the motors itself, and the Arduino Nano. And here you got your LCD screen. So you have your power bar. Oh wait, no, this is for transmitter. We have two 10K resistors here, and we have our 10-200K right here. So this is basically just like in our DP labs. You just switch it, change contrast. And then here we have our drone itself. So this is what I was trying to talk about earlier with the power bar here, going through for all our motors that are connected to our transmitters, our diodes, and our resistors. And then we have our buzzer, and this is our transceiver here for our drone for communication, and this is our water blade here. And this is a 3.3 volts, 8 megahertz, and this is where our problem kind of came as a concern, because when we uploaded the program to the drone, Evan actually uploaded it yesterday, and when he did that, he got a blue screen, so his computer crashed, so there was something going on, so we're still eternally trying to figure out like what's the baud rate, stuff like that. I actually had some classmates earlier today telling me it could have been baud rate, but we actually double checked our phone and that wasn't an issue, unfortunately. So we're probably going to go further, take amp meter, etc. to solve our issue. And we're getting pretty close now. It's more or less just keep troubleshooting.
Yeah, like Dave was saying, I think going forward from here, we need to set it up to a digital multimeter and see the outputs of all four motors and see if it's out of sync or out of phase, because I think that might be what's causing this issue. But also just to quickly sort of describe our build here, we started off with a drone frame, and the guide that we were following was from a guy named Max Imagination Online. And he kindly gave us a free drone frame that you can make with popsicle sticks. I actually did it instead with cardboard sort of solidified around with super glue. So it's a very strong build. And then we see here we have two trays. So you have to keep the Arduino away from the radio transceiver chip because that could cause noise. So I have the Arduino Pro Mini up on the top, battery. We have the radio chip coming out of the back, and then the motor control board is in the middle. That has the controls for all the motors there. And then right under, it's hard to see here, but right under the Arduino Pro Mini is the gyroscope, so it can stabilize itself in flight. There's a quick picture of sort of the coming steps of the project. We have the drone frame together with all the motors connected. Now the motor control board, this was all each specific line here is for each motor. So there's back left, back right, front right. And the outputs from the end diode, so the electricity flows in this pattern. It goes in, up, and then out the diode. So the diode polarity is this way. So this output from the diode goes to each motor, and then the output from here goes to each analog pin on the Arduino. So basically what the code is doing is, depending on what motor needs to be on at what moment, the Arduino will send a 3.3 voltage to the given chain, and then that will power on the motor. And you can see them here. We have all four just coming in here, and we have all four inputs right here, sort of hidden away there. And here's connecting it all together, testing the motor connections with the motor control board. So these were all soldered together, so we had to make sure that the soldering was clean, that there was no, actually just go back a second. We had to make sure that the soldering was clean, that there was no bridge connections. So all of these cannot touch each other, obviously. So here's our ground line, here's our power line, and none of this will be able to interfere with each other, or it would short the circuit out. So go to the next slide again. So we wanted to test that. Here's the motor control board with all four motors, and each line here is sort of the lines I was saying that get connected into the Arduino here. And if you just hook up the power to 3.3 volt power supply and then individually give them each power, you can they start to spin. And here's the Arduino Pro Mini. So it's a much more compact form size of like the Arduino Unos in our course. But it works the same way. There's 13 digital inputs. I think there's 8 analog inputs. And here's all the wire connections here before I connected it all to the other the components. And the frame, Max Imagination, the guide we were looking at, they also gave STL files for 3D printing. So we managed to 3D print this case, the cover and the case. So basically an overview is like the on switch would be here, the Arduino's up here, so you'll connect it in through there. The charging port for the 2 LiPo cell batteries are down there, and then the joysticks on either side. And here's the completed transmitter. It's not all in its case yet, but it does work. You can sort of see in the picture here the red light of the Arduino, the red light of the radio chip. So basically, once this initializes, this radio chip right here will broadcast at a specific rate, or it establishes a pipe connection, which Andrew will sort of talk about in a minute. But it establishes a pipe connection that this radio chip on the back here will connect to, so then the joysticks and all the inputs will be sending and transceiving to each other.
Yep, so here's some sample code for the drone specifically. So, as you can see right here, as Evan mentioned, the pipe address. So, the drone and the transceiver need to have the same pipe address in order to connect to each other. And over here, stuff like the radio, and this is all the input data. It's like the throttle, roll, pitch, and yaw. And here is an example of the transmitter code. So this sends the input data to the drone. And this is an example of the LCD and the same pipe address as usual. And if you go back for a second. So this here, this tells you the battery percentage of the transmitter, right, in volts. And that shows up on the LCD screen.
Oh yes, so for our future work, we want to add a first-person point of view camera to the drone. We want to also, so we also have some pins left on the drone, so we can add anything for like infrared, or add another camera to do a different option. And we also have, so for example, like color sensor, laser pointer, GPS, laser pointer is pretty cool, I really like that.
So to conclude this presentation, we have some physical considerations, sort of improvements that we want to do to this, because obviously, as this is the end of the DP course, this is not the end of this project's life. We're still want to work and get this flying. So we have some troubleshooting ideas, but some simple physical considerations, just sort of raising the legs so that the propellers are sort of over the main body to allow for an easier flight, and also so it doesn't get in the way with some of these wires. Strengthening the drone frame, it is pretty much strengthened, but I mean it could be more secure, sort of tying down these legs, and especially tying down these motors, because when these motors start to spin, they can rattle and shake, so you don't want them to lose the super glue connection and sort of just fall off. And wire management, of course, it's pretty manageable now, but these wires can be a little shorter, and you can sort of use a lot of tape and just tape them around the body. We want to continue troubleshooting this. Yeah, we're looking at getting a different Arduino Pro Mini, which in hindsight we didn't realize looking at it now, but it needed to be an 8 megahertz version, and the one I bought online, it didn't specify, so I'm unsure if it is an 8 megahertz version, so it might not be transmitting enough data to actually pick up the transceiver, because it does run, the code compiles, it picks it up, but then runtime is when it starts to get all the errors. So this might be like a 4 megahertz, or it's just not compatible enough. We might consider the reduced noise. This might be a factor. Adding some copper shielding around the base so the radio transceiver doesn't communicate with the Arduino. And adding some console logs to the code, which we already started doing to sort of figure out the issues. And it's clear that there is some sort of serial connection issue between the Arduino and my computer, the laptop. Thank you very much, and there's room for questions.
Hello everyone. So today we're going to talk about our project, which is development of an unmanned vehicle with Bluetooth controlled object detection using Arduino and ultrasonic sensor. So I'm Mehdi. I worked on the code today, and our partner Caleb and Nathan, they will talk about what they worked on. I'll go through Caleb first.
My name is Caleb, as he just said. Me and Nathan both collaborated both on the build of the robot. He purchased the parts because he has Amazon drop off at his house. I don't trust all Amazon stuff at my house. But he ordered the parts and gave them me and Nathan. Me and Nathan both collaborated on building the body, and then he worked on the code. And when we first started thinking of ideas for the project, we all agreed that we wanted to build a car that could move around in every direction and detect if there was an object in front of it. And we did some research on this, and Bluetooth controlled robots are used in educational and research environments. Like I'm sure you guys have seen it. Like I don't know if it's MIT, but it's University in Boston. They make robots and they're dancing around and use it. But those kind of videos intrigued us, and all the components used in this can be found on Amazon for fairly cheap, so we didn't need to break the bank to make it. And these are the main components. These are the foundation of our robot. The board we use is the Arduino Mega 2560. This is the brain of the robot. And we also have the HC05 Bluetooth module. This allows the car to connect to an app on our phone, which is used as the controller for the car. And we also use the L298N motor driver, which controls the motors, which control the wheels. And we also use an ultrasonic sensor, which is located on the front of the car, which detects if there's an object in front of it at a certain distance.
So for the system functionality, we are gonna use and showcase what it can do. For the first thing, so it can we can drive it with using any smartphone. Like it can move forward and backward and do a 360 wheel. So that's our wireless control. Object detection. So let's say we are driving it in a certain area where there is some object in the front. It will detect and give us a buzzer option. So it can do a buzzer option, and we can see it from, or hear it. So we did try to put it a second ultrasonic in the back just to go forward, backward. The problem is that it is a 4-wheel drive, and so it doesn't have enough power supply to connect two ultrasonic sensors at the same time. And as I already talked about our buzzer, that is audible, you can hear it from us, and the real-time responsiveness. Why it is matter? So when I started doing the coding, I found out that if I don't do a block coding in the Arduino, it drives the motor and then read the ultrasonic and drive it. Like it was like stopping, doing it and stopping. So I had to find a way to do a block system coding so that like they both run. That's another reason that why I can put two ultrasonic sensor, because they can do at a simultaneous time. So I have to do it with one time. So this is our coding. So in the coding, you can see that we have our front trigger, which uses the ultrasonic sensor. We have our buzzer pin, and we have two side of motor, because I put right side and left side together so that like I can do a 360-degree or like left and side and front. And we have like this board check obstacle system, which check the like obstacle and give us a buzzer, and it is the reading section over here. And this section is just all of the motor section, which reads and give us the option from our Bluetooth system that goes from our smartphone, go to Bluetooth system and drive the motor.
And some of the hurdles we faced during our project were when we first decided to do the RC car, we were looking into parts and the components that we needed. And with the Arduino kit that we purchased at the beginning of the semester, we didn't have every part that we needed. So we had to go and find some parts online because they weren't available around the town. And then with the parts, we had to make sure that they would fit in the housing of the car, because our car is only so big. And if we bought a part that was too big, it just wouldn't fit, then we couldn't really make it work. So when we bought the power supply, we had to make sure that it would fit on the car and it was stable enough for all our components to be powered at the same time. And for the code, we had to debug the code because we needed real-time responsiveness so that it will beep and it will detect other things that it's coming into contact with. And balancing this project with everything else we had going on was also one of the big things. And this is just a top-down view of the car. It's pretty much the same picture we had as final product. It's just I don't think we had anything soldered onto it yet. But this is just the same picture, it's just everything is soldered and it's all working and functional now. And for the future works of this, we could add more sensors so it has like a 360-degree detection, because right now we only have an ultrasonic sensor on the front. We would just have to add more power supply, a bigger power supply. And we could add cameras which would allow for audio and visual detection with the card instead of just the audio that we currently have. And we could improve the mobility, as right now it's sort of robotic-y, like movement. So you can make it so the motors are more precise for movement, and you can add suspension so that when you're going over terrain and stuff, it's not like just a forward. And for the power optimization, we think we could incorporate solar panels so that the power, you wouldn't need to use such a big power supply, and you can generate the power in the system itself.
So that's everything from us. If you guys have any questions or any concerns, we're ready to go.
All right, hello everyone. My name is Joshua Shears,
And I'm Cameron Reese.
and we're going to be going over our Arduino Jeopardy game. Now, in terms of what we did, a lot of our stuff was together. We got together and we worked on the project together. There's not too many pieces and parts, as it only just focuses on obviously the Arduino sketch code that powers the Arduino, and then the Python code, right? So a lot of our stuff was done together.
Alright, so a little background. So what is Jeopardy? Jeopardy, of course, is an American quiz show. Players choose from questions and categories based on the dollar amount, which is based on the difficulty of the question as well. Once all the questions are answered, you get a final Jeopardy, which allows you to either bank all your money, some of it, and you're either going to lose it all if you get the question wrong, or you will double it if you get it all right. And then, of course, the components that we used Python for the actual GUI. With that, we used Tkinter. Then we used Pandas to import our Excel sheet with all the questions and answers. And then, of course, Serial for the Arduino to actually connect to our Python, and threading as well, so that they both work together. And then time would be used for, of course, setting boundaries for the code to actually work, and then your limits for the questions. And then with our Arduino, of course, we have the rotary sensor to let you move through the GUI, along with the buttons to let you select which question you want to pick in the game. We have our LCD screen, which displays the amount that you have currently, and then our buzzers and red and green LEDs to show if you got the question right or wrong. You'll see here that the code is green and red. That shows the difference between the Arduino and the Python that Josh will explain on.
Yeah, so with the red we have the Arduino, and the green we have the Python. So first things first, it starts off with a handshake agreement. You have the Python code is going to be starting to listen for the Arduino to make sure when the Arduino is ready, it'll send a ready state, and then the Python will return it. Upon that, the Python GUI starts, and it then senses the rotary sensor value. So it's constantly checking to see what the rotary sensor says, and the Arduino is sending it back to the Python. When that happens, the buttons in the GUI change. So it gets different buttons get highlights, and so you know that you're going to be choosing the right question. When you actually press the Arduino button, it will open up a question GUI level, and then the Python will send out the GUI level change. This is just a string that tells the Arduino that to switch the button commands. Because when you go in and press a button in the GUI, it will automatically sense that when it opens up the new GUI level, it'll automatically sense that question's been answered and just go. So we had to make a different button press. We'll go over that in our problems in a little bit. But yeah, buttons pressed, and then the GUI answers. It'll give you the correct or incorrect and how much you won or lost. Then there is the buzzer and LED answer. You have like the green and red buzzers that we have, the green and red LEDs, and the buzzer will tell you if you're right or wrong. Then the Python will send the money value into the Arduino, so it shows up on the LCD display, and of course then the Python will send back another level return, which will send everything back, so it'll all start working on the root level again, the root layer. So a couple of hurdles that we end up coming across was the connection between the Python and the Arduino modules, specifically because I have the growth kit. The growth kit is a great piece and it's helped us a lot throughout this project, but not a lot of the Arduino or the Python modules and libraries were able to really work with the growth kit, and the ones that did were not compatible with Windows. They were only compatible with Linux. So we had to figure something out, and PySerial ended up coming up, and that just takes everything, it just responds to everything via the sketches that were sent into the Arduino, and goes based on that. So then we also have the GUI control. This is where the bulk of the problems lie, specifically in the switching to GUI levels. When you first start up the game, it starts up with an initial root GUI level. This level is then affected by the Arduino, the rotary sensor, and the button. But when you click the button and something came up, what ended up happening was the button press command would trigger it again. So you would open up a question and it would answer it right away. That's the problem that we had for a little bit until we decided to go in and change it so that it's the Python code will send out a message and be like, hey, this is the different level we're going on, and then the button command will change from like new press, button press, bet press, and it's just different strings that we'll send out so they each know which one they're talking to. And of course, button highlighting. That one was a bit of a thing to figure out, so you know all of the buttons, or you know the button you're about to press every time, and because it will end up changing colors in the GUI.
Future work that we want to do, we want to have separate player scores that show up on the LCD, so player 1 has X amount, player 2 has the other amount. It just adds a competitive aspect to the game, adds more fun to the game as well. We want to add a title screen, so when you open up the game, that it actually shows up with the Jeopardy logo, and you'll be able to change your settings there as well if you want to make some categories worth more, some worth less, if you also want to change the name of the player that you're using. And then, of course, we want to add more questions and categories, have that 5x5 Jeopardy screen. We have a 3x3 right now, and then when we have those more categories, you'll be able to choose for different ones, and then depending on what your knowledge level is for each one, you can go through that as well.
So really, in conclusion, microcontrollers are found everywhere. It's in our gaming controllers that we play with. Microcontrollers are a very unique and fun piece of tech that can do a lot of things, and it's very enjoyable to work with.
Another thing we realized, Python's decanter not made for making games in the slightest. If you want to make a game, just go use Unity or Unreal Engine.
Yeah, and this would be a continuous project. We had a lot of fun doing this, and we want to continue and actually build the future project thing because it was a lot of fun in the end. And thank you very much, and we'll give it a demonstration. So, you guys, I'm hoping, I picked categories that hopefully everybody might know some stuff. So, here we go. It says Arduino's ready, handshake ready, and as you can see, it's continuously reading the rotary code there, or the rotary sensor. And if we twist the rotary sensor enough, it'll cycle between each of the questions. And then all we have to do, so who wants to, which should we go? Who wants something? Raise your hand. Like, pick a category, pick a number. What do you want?
What are the categories?
Oh my god, alright.
Pokemon, Muppets, and UFC.
UFC.
UFC, alright, 100, 200, or 300?
300.
300? Alright. And up comes the multiple choice. So, the fighter that became the first woman to win a UFC title dominating in the bantamweight division, Ronda Rousey, Amanda Nunes, Holly Holmes, or John Jones?
John Jones.
John Jones. You guys want to go John Jones? Alright. Sorry, it's incorrect. As you can see, the LED goes off and the buzzer goes off and you get a noise sound. So let's just go through a couple because I don't want to take up too much of the time. Yeah, this fighter is known as the Notorious and has held featherweight, UFC featherweight, and lightweight titles. McGregor, right? There's the right sound. You get 100. So let's just go through a couple, get them done here, because I know I want to use up too much of our time here. Yeah, his nickname Bones. Of course, John Jones. Just want to go through these real quick. There you go. This is the person that Elmo hates most on Sesame Street. It is Rocco. Michael Caine. No, he hates the Muppet the most in Muppet's Christmas Carol. The Muppet is large, furry, and monster who loves cookies. I wonder who. It's gonna take a bit, sorry for the time there. This green Muppet is known for being, it's not easy green, and is the face of the Muppets. Big Bird. Big Bird, Oscar. Alright. This one I'm going to get you guys to actually do. This legendary Pokemon has the ability to control time and is primarily colored as blue.
I was gonna say Dialga. I think Dialga.
You are correct. It is Dialga. Celebi is also a time Pokemon, but it's just not blue.
Dialga is space. Dialga is time.
It is time, yeah. Yeah, first Pokemon in National Pokedex.
Bulbasaur.
Bulbasaur. And the easiest question, I think, is this one. Which Pokemon is known for being Ash's Pokemon?
Mimikyu.
I heard Mimikyu first. As you can see,
Close enough.
As you can see, the Final Jeopardy button comes up, and it comes in. Category is superheroes. Now you guys can't see it very well, but you can get the betting amount on the phone, on the LCD screen here. By the way, all of the player points and stuff has all appeared onto this screen.
All in.
We're going all in. All right, all 1,000 points that we have. Who is the best superhero?
Well, what is that?
It's complete. I know, right? It's not a fair question at all.
Spider-Man, but
John Jones.
John Jones?
I think he is Spider-Man.
Batman.
He doesn't even have any superpowers.
He is correct. It is, in fact, Batman, because
See,
he's a tech
it's
guy.
Batman.
And of course,
It wasn't John Joe.
everything shows up on this, and we can just go and end game here. It's a little bit finicky, something I need to still work with there. There we go, and end game. Thank you very much.
All right, good morning, everybody. I am Ava Dooley, and I was mainly working on the software for our project.
I'm Olivia Lai, and I mainly worked on the hardware aspect of our project.
So, our Morse code translator application was designed as a byproduct of wanting to combine the traditional Morse code communication with a modern delivery method and display method via the Python GUI. A lot of our projects this semester had a lot of structure and a lot of rules that we had to follow, so we wanted to have fun and put our own little creative pizzazz in our project, so labor of love. This project is called From Knowledge from POSIX operating systems, as well as our digital systems projects and our active circuit applications for the general knowledge of placing components on our breadboard.
Okay, so the hardware components that we use in our project, we used an Arduino Mega, the USB connection to the laptop, jumper wires, push buttons, LEDs, resistors, a passive buzzer, the LCD display, and a potentiometer. So as you can see in the schematic, we have our Arduino Mega here. You can see the jumper wires connecting everything. And then we have our potentiometer over here, which controls the contrast for the LCD. And then we also have 4 resistors. So they're each 220 ohms, and they control the current flow to the LEDs and the LCD display. We also have 3 push buttons. So the first one here is for the Morse code input. The second one functions as a space bar. And then the third one there is a delete button. So if you make a mistake, you can press that and it'll just delete your last inputted character. And then so we have our passive buzzer over here. So that kind of works hand in hand with the push buttons. So it'll make 3 different sounds. So it'll make one sound as you're inputting the Morse code characters, another sound to indicate that it was a valid input, and then a third sound if it's either an invalid input or if you press the delete button. We also have 3 LEDs. So the yellow one lights up as you're inputting the Morse code characters. The green one lights up to indicate that it was a valid input and that it's ready for your next character. And then the red one lights up if it was an invalid input or if you press the delete button. And we also have our LCD display. So as you're inputting the Morse code characters, they'll be displayed in English text here along the screen.
All right, so the software really bridged the gap between our Arduino circuit and our design idea. So we used Arduino code as the absolute base of our project. And the Arduino code was responsible for determining the dots and the dashes, and it was responsible for keeping track of the internal state machine via the unit of time that we defined. And it also provided the input for the Python code. And the Python code was actively listening to whatever the Arduino code sent through the serial port, and it had to operate synchronously because you can only send direction, you can send it both ways, so it's bi-directional, but you can only do it one way at a time. And we also implemented a GUI for a sleek modern design. So this is the integration of the serial port within our Python program. We have the output here that lists the current working directory that you're in. It lists all of the attached devices to the computer. You can select your port via the number, and then it'll tell you what you've selected. And it's important to note that this is only for Windows as of right now. We had some troubles getting it to work on Mac, but on Windows it runs on any machine. So it's easier to do our little demo to show you what it's all about. So upon running our Python code, as I just explained the input, this should come up in a second. So to give you the current working directory, and obviously we only have one thing connected. So we're going to select the port, and upon selecting the port, as you may remember from the welcome screen, it displays Ava and Olivia's Morse code translator, and then following a ready prompt that will clear the screen once you start inputting, but it just lets you know that the machine is ready to take the code. So it displays the message across the screen and begins to run the GUI. So after the ready prompt is up on the device, we can start writing our Morse code. And we have a nice little chart here because even though we've written so much Morse code doing this project, we are still not good at Morse code. So that's when there's a valid input. Our space function. And if I needed to go back, then I press the delete key, which triggers the low frequency tone. So I'll just quickly type out our message. Our system operates at about 5 words per minute to allow for inexperienced Morse code users. And that's me being bad at Morse code, but responded to the input. And automatically, when you input any punctuation into the Morse code, the Arduino will send that along the serial input, and it will go into the Python code to be processed by our process sentence function. So we have 2 main threads in our code. One of them is going to put the GUI on the screen and keep all of the rest of the thread behind the code. And the second thread is going to take the string, take the characters, append it to a string. It's going to filter out the underscores, put in spaces so it formats it so it's an actual sentence. And then immediately upon creation of the button, it will place it in the window and pass it to our text-to-speech function. So our text-to-speech function translates whatever is written in the string, and it's going to append it to a list of strings in order to keep track of all the MP3 files created in this current session. So for example, I can go into my current working directory and I can see on the screen that we have our MP3 file in there. However, with repeated testing and figuring out how this is going to all integrate with each other, we noticed that we had a lot of wasted space and we had to go through and manually delete all these MP3 files. However, upon appending the file names to a list, we are able to just delete the cache, and any and all MP3 files created in this session will automatically be cleared out. So just a little garbage removal method. We also have an additional text input for testing purposes if you really wanted to make sure that the LCD display was displaying the text. So we just put in a few test sentences that would speak as the Python text is displayed across the LCD screen. And by timing it, we're able to get it lined up pretty well, so it reads as the words are going across the screen, and it's pretty well timed. So switch back here. Second to load. All right.
Okay, so some things that we did to make our Morse code translator original. We have a parallel circuit. So we used our knowledge from most of the labs in this course to create our own original parallel circuit. Also with the LCD display, as you can see, as you're inputting the Morse code on the Arduino, it'll actually display it here. But so the full sentence of this is Ava and Olivia's Morse code translator, but you can see that there's not enough room to display that full sentence. So there is a scrolling feature, so as you input the next letter, which would be an M, the A here will fall off and all of the characters will move up and then the N will appear at the end. And we also created a Python GUI. So once you're finished inputting the Morse code on the Arduino, it'll send that to the Python GUI where it will then translate it into English text and it'll appear as a button. So you can click on that button and it will actually announce the sentence through Google's text-to-speech API.
So a lot of our work came from the multi-threading in the Python program. So like I said, the first thread was to display our GUI, dynamically create the buttons, and send the text-to-speech to the play sound library and play the sound. Additionally, with the text-to-speech and clear cache feature, they kind of go hand in hand. This was a custom method that we designed to use the OS library from Python, as well as the Google text-to-speech API library from Python, to keep an array of all of the raw sentences, so invalid characters are filtered out, so making the files and creating the file names, you wouldn't get any errors or exceptions from that. So those are just some methods that we spent a lot of time creating and were absolutely original to our project.
Okay, so some challenges that we faced while we were creating our project. We originally wanted to implement Bluetooth, but we were unable to find the HC5 Bluetooth module, so we couldn't do that. We also had some issues with the LCD because of a faulty jumper wire. Because the LCD has 10 pin-out connections, it was a bit difficult to actually figure out which jumper wire was causing the issues that we could replace that. And there was some trial and error with the software implementation. So we were originally unable to send complete sentences through the serial port. So it would actually take the first character and receive that as one sentence, and then it would take the rest of the word as a separate sentence. So to fix that, we had to send each character individually. And some future improvements we'd like to make to the project. So we would like to create an iOS application, so then you could access the Morse code translator on your iPhone, as well as the Bluetooth implementation, so you could connect wirelessly to a phone or laptop. A backwards encoder, so that would allow, once you've inputted the Morse code on the Arduino and it's been sent to the Python GUI, it would actually allow it to then translate the English text back into Morse code and send it back to the Arduino. And also a 9-volt speaker on the Arduino. So right now with the Google text-to-speech API, it will announce the English text once it's been translated, but it's just through the laptop speaker. So we would like to have a speaker directly on the Arduino that it can use to announce the text.
So in conclusion, we were super happy with how our program turned out. We were able to bridge that gap between the traditional methods of communication, which oftentimes resembles computational language like binary, dots and dashes, zeros and ones, and we were able to implement it in a sleek, modern GUI design. We were able to combine the use of hardware, such as in our course, with concepts that we learned in POSIX, as well as explore multi-threading and expand our knowledge about how the serial connection works and that bidirectional transfer of data. We achieved our goal of receiving the real-time translation to Morse code and displaying it on the LCD screen with feedback, and our text-to-speech option, which I realized that I did not demonstrate because the laptop is muted, so we will do that right after we finish our presentation. So thank you all for listening.
Good afternoon, everyone. My name is Heath, and this is Devin.
And today we're showing you our advanced Arduino metronome that is a versatile tool for any timing application, but we just broadened it out with metronome. We have our background and description here. So basing it off of a traditional metronome, looking at one, you can kind of see that they have a very big lack in flexibility. They do one thing, and that's tick, back and forth, doing the same with slightly changes in their beats per minute. There's little to no visual feedback. You can't visually see when it is ticking. You can't really know what's going on. And then you can't be precise to the exact beat per minute with them, as it's just a little tiny clock going back and forth. But with ours, we have a very customizable beats per minute, getting it down to the exact beat per minute, with synchronized visuals and a real-time LCD display.
So I worked on the hardware mostly. So what we're looking at here is we obviously have the Arduino board. It's a 2560 mega. That acts basically as the brains, the calculations, the timing of the whole thing. It takes care of the user inputs and obviously the outputs of the buzzer and the lights itself. We have LEDs. Each one corresponds to a different setting. So there's obviously presets with specific metronomes and the types of beats per minute they have. They have names. They're called, I can't pronounce them. Allegro, Allegrato, Moderato, and Andante. So each one corresponds with a yellow, red, yellow, green, and blue light. Obviously, red being the slowest, and then green being fast, and blue being the fastest. And then we have a white LED here as well, and that basically corresponds to the custom ones that don't fall within the range of those musical sort of presets. We have an LCD screen here, which will display what setting you're in, as well as your exact beat per minute, and if you do happen to go outside of those presets, it'll just say custom on the top there with your exact beat per minute. These two potentiometers, one here is to control the contrast of the screen, making sure you can see it in lots of different light conditions, as well as this potentiometer right here, which will take care of your exact and precise beat per minute settings that you require for whatever application you're using this for. And just to mention here that this is not only for musical settings, it can be used for scientific experiments. It can even be used in hospitals to track beats per minute of CPR or any sort of thing that would require a beat per minute. And the buzzer, of course, you need an auditory feedback just to make it a metronome. So this buzzer obviously will buzz on each beat per minute in sync with the LEDs as well.
I more so worked on the software side of things. Here you can see like our key software features. I kind of added a flow chart here to show that we got our start, and it's really just an infinite loop, and we have our 3 to 4 major functions right here. There's obviously more to it, but basically we are starting off getting the beats per minute by using calculations and determining based off of the position of the potentiometers. And then based on that, if the new position is different than the old, depending on if you're in a new preset, in a custom, it's going to need to get the new name, update the screen, and so on and so forth. And then in doing so, you can see here, we have our board with our 4 mains. I couldn't fit everything onto this screen, but because I wanted it to be somewhat visible for everyone. But seeing here, you can see for our update LCD, we gotta set our cursor to the start. We got our muted setting here, as well as saying 0 beats per minute if there's nothing, and just clearing it and reprinting it if need be. And then over here, you can see we actually don't have a set instance for each LED. It's just one value, and it gets changed based on which one is active. So you can see like the active LED 4 value gets changed to 4, it lights up the blue one, so on and so forth, depending on the name and title to it.
So looking at our original contributions, the key benefits of our metronome over regular metronomes, we have 2 potentiometers. So as I mentioned in the hardware side of things, we have 2 potentiometers here, one that will take care of the contrast of the display, making sure it can be seen in lots of different light conditions.
And then here we have, you can see the integration of the visuals here as it beeps with the buzzer.
And this one here is on custom because I haven't actually made it to one of the preset settings yet. And then as you can see here, the further I go up, there it's at my slowest preset setting. and then as I turn this, it is going up by each individual beat per minute, which gives us far more customability than original metronomes. And the faster I go, it'll keep going through the preset lights there, making sure that people are actually able to see and making it very accessible to lots of different people that may not be able to hear as well, but still need a timing device.
And as of right now, we have it set to only be in between a range from 40 beats and 175. Now, we can have a much broader range if need be, but we just felt for this simple demonstration that was the easiest go-to range, allowing you to have a custom setting as well as your 4 main preset options when it comes to anything musical. So here we have our initial design of our LED screen, which did not go quite according to plan. We could not function with the LED screen without connecting a potentiometer to it. It required one. If we didn't, the LCD screen would not let us change its contrast. It always kept resetting. So we just added a second one. So now we kind of fixed the problem and made it better, because now you can change your brightness, dimness, or so on and so forth, and change your beats per minute.
We also had another issue with the LED timing. So when we were setting up the LEDs, the wiring went fine, of course, setting up an LED, not too difficult. But there were delays in the synchronization, so as you were turning the things, they would turn on after you got to your preset setting and then stay on the whole time. So by the time you were done using it and got through all the settings, the lights were just all on and stayed on. So basically we just adjusted the software to basically be more precise with the timing, so then obviously they can now beat as the beat per minute is there, making it extra precise.
And then for the future with this project, we had a lot of ideas with replacing the potentiometer with the rotary encoder. We originally wanted to do that, but it required, we wanted to have the buzzer working, the rotary working, be able to change it for you to show you. So we opted for the potentiometer for the time being, as it's the more simple option, allowing easier encoding and such. But the rotary encoder would allow you to have a broader range, more precise accuracy, and so forth.
And also a lot more input with one device, because it also has a button. So then you could be twisting the thing to actually edit your beat per minute at 1 beat per minute intervals, but also push the button to go between each presetting instead of having to just dial through each one. And obviously that would make it quicker and easier to use. So that's definitely something we'll look at in the future.
And we would have loved to have designed the protective enclosure for it. We didn't feel it was necessary for this demonstration because we wanted to be able to show you everything. You could see all the wiring and such. But if we were to kind of have a broader range with this, show it outside this classroom, it would be better to be in an enclosure to be safe. And an addition of wireless connectivity would be nice to allow you to control the beats per minute that's being displayed and the sound that's being displayed with your phone, be able to have your own kind of potentiometer on your phone.
Through the course of this simple yet versatile Arduino components, which obviously included the LED buzzer and LCD display, our metronome actually achieves precision that is beyond most regular metronomes, only because most of them actually work with a wind-up thing on the back, and they're all mechanical, so as wear and tear happens, they become less precise. So if you need something extremely precise, going with something like this is definitely the best way to go. Its modular programming makes it so adding features and removing features when needed is way easier, and it makes it a far more expandable design to provide opportunities for enhancements in the future.
All right. So for our project, we made a sonar, and we should introduce ourselves. So I'm Ryan House, and
I'm Patrick Murphy.
and so we split up this project, mostly working on both hardware and coding together. So we're just going to go back and forth, do it on the slides.
Alright, so some background. We wanted to make a sort of radar adjacent device, but using an ultrasonic sensor instead. So to do this, we use the Arduino Mega that we got in the kit that we got for the labs, the ultrasonic sensor, the servo motor to actually rotate the ultrasonic sensor. And we also added a dot matrix board as a way to visualize what the sensor was recording for ease of use. And a good note is that this could be further implemented for many different cases.
All right, so the way it actually works is once it powers on, the servo motor starts and it'll consistently oscillate between 15 and 165 degrees. While it's doing that, the ultrasonic sensor it keeps reading data and reading the distance, and it takes the angle of the servo motor and the distance and passes that over to the stereo port, and it uses that to give us feedback on our dot matrix, as well as we have a GUI that has it kind of tracks the radar screen as well. And so we have that kind of on the next page there, as an example of what that looks like.
Yes.
We had a video.
I got the video. So this is a video of it in operation. This would be on an external display that you would connect. And as you can see, it's not playing on that screen. One second.
But essentially, as it runs back and forth, it just
Yeah,
kind of
there you
reads
go.
that data.
So it's highlighting anything that is coming in range of the ultrasonic sensor in red, and if the area is clear in front of it, then it highlights it green. Okay, so as far as our original contributions, so we also have this dot matrix board that's attached, and this will also display in red LEDs what the ultrasonic sensor is detecting in front of it, so it gives the user direct feedback in case there isn't an external display available. So this also had to be wired and coded for implementation for it to work. Yeah, and it's useful in case when an external display is not available.
So when it came to the hurdles we ran into, a big one was you can get, there are brackets you can get like a 3D printed bracket that kind of combines the servo motor and the ultrasonic sensor. We weren't able to kind of get one of those, so when it came time to building it, we went through a couple different designs on actually how we can kind of make one, just say with cardboard, but all the designs we tried, they just, it wouldn't balance it properly, and then the sensor wouldn't kind of read properly. So we went through a couple different designs. What we ended up doing is just gluing the ultrasonic sensor right directly to the servo motor, and then finally we were able to kind of achieve a bit more of a consistent result, because that was the big problem. We've got a specific range that we're covering, and if there was any kind of drag on the motor, it would kind of mess up all the calculations. So we had to innovate, keep it simple, and glue them both together.
In terms of future work, I don't think either one of us plans to implement on this any further. We kind of just got what we wanted out of this project for sure. But it could be further upgraded to trigger other components. So this could be useful in cases where you have someone who's hard of hearing and you need to get their attention. This could be connected to an LCD or a LED in their room, so that when you wave over the sensor, it alerts them that you want their attention. Or also in workshop examples. So if someone's operating a power tool and they have headphones on and someone comes into the room and walks up behind them and startles them, this could lead to an accident. So if you have an LED connected to this, so maybe when the door obstructs the ultrasonic sensor, that person is then alerted that someone has entered the room, and they should be aware.
Absolutely. All right, so in conclusion, this was a fun project to kind of take on the back of what we covered in our DP exam, or labs. You know, we took a couple of different sensors and see what we could do with them, and the sonar example was kind of, you know, really interesting, what you can achieve with just a couple of these sensors. And we had a lot of experience with, you know, the challenge of kind of implementing our code and trying to get that dot matrix to work and render the radar screen. And all in all, it was a pretty valuable kind of design experience.
Yeah, so we could, I'll show you here, like it working, and it might be hard for a lot of people to see, but. So once it plugs in, it resets, and now it's rotating the servo motor, and then if you place your hand in front of it, the dot matrix updates with the information that it's being blocked in that particular spot.
In transit, getting it here, unfortunately, the sensor kind of tilts it back a little bit.
Backwards.
Ideally, it's nice if it's kind of straight on, you get more of an accurate result. But yeah, it will pick up if there's an object in front, and it'll display it to the board. And there also is, like I said, what we showed before, there is that radar kind of GUI as well that we had the example of before. So those both render in real time.
Yeah.
All right.
Alright, so this is our system, the automatic plant watering system. And I'm Luke, this is Josh, that's Jordan. And we wanted a simple project, and we came up with the idea because my dad always complains about having to water his plants. And we were looking for a solution so he didn't have to do that anymore. So the system's small, inexpensive, pretty simple parts because we can't have something too big. As you can see from what Jordan's holding right now, that is the entire system because it needs to be reproducible. Because most people who have plants typically have more than one. So usually you're going to be using more than one of the systems. So you either need to be able to adapt the system to have multiple tubes, or you need to be able to just make more of them. So that was the goal of the initial design. We used Arduino for the brains, and the circuit is on the inside of the box if Jordan wants to open that up. We don't have a plant cup with soil today because last night our pump unfortunately broke. That just teaches us to choose our parts more wisely. But yeah.
For the overview of this, we use just mainly these 5 simple parts to make our project. The Arduino board, the moisture sensor, the water pump, a 5-volt relay, and a battery module. With these 5 components, we made it a fairly simple circuit on the inside here with all of those, and it takes up very little space, as you can see. So if you need to hide it behind one of your plants, it's pretty easily done.
And the way the circuit works is actually very simple. This goes into your soil. It sends a signal through to your Arduino, which will determine whether it needs to be watered or not. It sends a signal out here to this relay, which just gives power to the pump in the reservoir, and it'll pump water until it tells you to stop.
Alright, so yeah, our pump broke, but we did actually have some videos of the system working. So the first one literally just shows the sensor is out in the open air. There's no moisture, so therefore the pump knows, okay, it's time to shoot water. And this is also designed in multiple ways to where you can have it plugged into your laptop, you can have it plugged into the wall, you can run it off a battery. As you can see here, we have it plugged into the wall with a simple USB block that everyone usually has at home. They're pretty accessible, and the pump will turn on. I don't have sound in the video, but the pump is on. That's where it actually is.
Just try to turn on the laptop here and volume on.
No, not quite. This is a presentation. But you can see in the previous video that it was working.
So the objectives of our project is to create, obviously, the automated watering system so that Luke Stad does not have to worry about his tomatoes anymore. He just needs to keep the water supply full. The circuit is very easily accessible as just flip off one little flap and you can access it, you can mod it any way you want, you can improve it, you can make it so it's operational on multiple different plants.
Something like your pump breaks, you can replace it.
Exactly. The code it was a fairly easier code that we use so that if you do need to change any of the moisture levels, it's a very simple task because each plant obviously needs different moisture levels to thrive. Some of the problems we had with this was when we first implemented the circuit, we tried to use a breadboard. But with breadboard, it takes up way too much space in our little box we have here. So we decided that it'd be better off not using it. The pump that we have that now doesn't work relies on a battery pack. That was unknown, I think, when we first were.
Yeah, we weren't planning on using a battery pack at first, but then we decided to implement it later because one, it's more reliable to use 2 AA batteries, and 2, because then it gives us the ability to use it wirelessly.
And we also had the problem of making sure that we keep our system dry, because if any leaks happens, well, the whole system will not work, because we all know how water and electronics goes.
So these are the decisions we made throughout the entire process. Now, this is the original, the concept circuit that we were basing our project off. It had the LCD, because originally we were going to do a plant health full all-in-one monitoring system, but then we found out with the shipping times of certain parts and also just the decision to have a small, more compact, reproducible setup that it just wasn't worth the risk. Well, not risk, but yeah, it wasn't worth it in the end. So we decided to go with a smaller setup that is more easy to use. It is easy to use, easy to reproduce. It can be done many times over and over again. And for the future, we could also, of course, add more pumps for more plants. We can actually add more tubes, some other ways to implement more plants into the system and have it, continuously expand and grow. And then the Arduino in the center actually should be able to operate off the brains for multiple plants as well.
Conclusion, there were a lot of problems, but in the end, well, we didn't make something that works, but we made something that worked for a little bit. Yeah, until it broke. But it was fun to learn. The building was very, very challenging because there was a lot of soldering involved, but
There's a few less parts than we originally intended.
Yeah.
Using everyday home. And also, I just wanted to point out the workload split. So I worked on most of the code of the operation. Josh picked out the original circuit online and he picked out the parts. And then Jordan did a lot of the testing and he was the one who had to suffer through dealing with everything at home when it all went downhill.
soldering.
And he did all the soldering, yes, because in our circuit, instead of using a breadboard, we were soldering our pieces together. We would strip the wires and we would just solder them together, simple, basic stuff. And that's how we operated the circuit. And here are some references, because this project's been done many times before for different reasons and different purposes. And these are the references we used. We were basing it off of these guys that we found on Arduino and Tinkercad, and that's pretty much the end of it, yeah.
That's it. Thank you. Thank you very much, guys.
Okay, good to go. Okay. Yes. Hello. This is I'm Josh, and this is my my project. It's an Arduino-based alarm clock. So Arduino is a platform which enables the create simple service projects such as this one, and this project is pretty much a combination of pretty much every single thing that we have. Not every single thing, but a lot of stuff. All the stuff that's in there is what we have used or done in the lab. So the stuff that we've used was an LCD screen with a potentiometer, an ITC module, which is a real-time clock module, a buzzer which will sound the alarm, and 4 push buttons for the different features. So the LCD screen will display the time and the time in which the alarm is going to be set to, and the ITC module is what the time is getting extracted from. The buzzer is a passive piezo buzzer. at a phase when the alarm time is equal to the clock time. Its sound is a 1000 hertz noise and is activated by pressing the push button next to the LCD screen. So there's 4 push buttons, like I've said, and I'm just gonna go through left, and the order is from left to right. So the first button is the set button, which when pressed enters the alarm setting sequence. The first stage adjusts the hour, then adjusts the minutes afterward when you press it again, and then the circuit will confirm the changes and returns before we decide the stage goes back to normal. Push button 2 and 3 is the up and down buttons, which are like when you're in the sequence of like changing the alarm time, it lets you go up and down the clock respectively, and the stop alarm button is when the alarm is sounding, you press the button and it stops the alarm. Let me do a demonstration. I have my camera. I don't know if this will work with the presentation, but okay, is it, hold on. Is it, it's not showing me the thing. Oh, I apologize. Oh, here it is. So I have the camera here. It's just to give you a better view. And, oh god. Oh no. Something happened.